13th and see what they do. Okay, so I'll start in a minute. I may just walk up and down the hall for a minute if y'all don't mind. I went ahead and started the stream. Maybe I shouldn't have done that, because sometimes it gets attached to the old stream. So let me make sure I didn't goof that up. Oh, it didn't. Okay. Okay, so I'll come back in a minute. I'm just going to paste the floors. So some places have a water refill bottle where you can just put the bottle. Do we have one here? I don't. Or do I have to go to? I know there's some in McKeever, but I don't want to walk that far. Huh?
X too broke. They can't afford that.
Don't you pay them enough money?
Yeah.
Anyway.
Pay them more than enough.
I know that they installed a couple in McKeever, but I don't know. Maybe there's some in that building, but I'm not. I'll just walk. I just won't talk much. How about that? Okay, so I'll be back in a minute. I'm just gonna walk for a second. We got 5 more minutes. Well, do y'all mind if I go ahead and start? I mean, it is being streamed, so if somebody comes in late, they can always go back and look at stuff. Okay, so I'm putting up the paint thing so I can get a white background. So, scalars and vectors. Okay, so of course you've already had something like this somewhere. I mean, probably in physics. So scalar is nothing more than a number. Vector has a direction associated with it. In other words, okay, I'm not a great drawer of, but say we're right here in Rothwell. Somebody says they're hungry, even though, well, I guess it is 11. And somebody says, okay, the lunchroom is 500 foot away. So if you're doing that, 500 foot is nothing more than the edge of a circle. So if half of us left, I mean, we'd be going in all different directions. We wouldn't know where to go. Some of us might end up at the Whataburger over there, but I think that's further than 500 feet. The people that end up here would end up being able to eat. They used to have food over there, but I don't know if they do anymore. So people are walking at random. But you've seen this kind of stuff before: north, okay, east, and west, and then south. I mean, actually, I guess you don't need but two of those. For an engineer or a mathematician, they'd get rid of this one and get rid of that one, and then just call that X and call this Y, and forget the rest. And actually, if you do directions, some people will do directions and then north, northeast, 30 degrees or something like that. If you look at navigational charts, there's an angle associated with it. So they'll give you directions and then an angle, meaning, you're heading this way, say maybe 30 degrees. So the vector has basically a basic direction associated with it. So what I mean by that, if somebody said 500 foot south, then think of it like this, okay? Here you are, and I go 1 foot this way, this way, this way, or this way. So if these are all 1 foot distance, that gives you the direction. If you pull out your iPhone, I think you can find a compass on there. Oops. And so if I do the compass, it's showing me north is that way. And so then, this is going to be, so, wait a minute, north. So it looks like he's doing north, and here's your angle. So this is a 0 angle. And he's, for navigation, you do due north, and then 90 degrees is east, so this is 90 degrees, and this is of course 180. And so navigation is slightly different than what we like to see as engineers. I guess if you flipped the axis over and you looked at it the other way, and then made that the X, you'd have the same thing. The key is you have a basic formation of a direction you go. Like somebody says, you go this way. Think of it like 500 feet times my finger is 1 foot long. I mean, it's not, but that's the basic direction or basis. So that's why we form out these coordinate systems that look like, hang on, and you've seen all these before. You form out a coordinate system. Usually in math, it looks like this, has a basis vector there, a basis vector there. And if you're looking for some vector, you might have 3i plus 4j. And you've seen this before, somewhere you've seen it. However, the first part of this section, he starts talking about just loose vectors. And he's, comes up with the formation, A plus B. So here's a vector A, and say you have a vector B, then A plus B is this. Now, there's a reason he does this initially, because it lends itself towards some problems, or solving some particular problems that are easy to solve this way and very hard to solve this way. But we find we abandon this fairly rapidly. And let's make up a problem associated with A and B and work our way through this, and we'll find the things we need thinking of it this way. So here's one way, and here's the other way. This is, I would say, going to be used a lot. All right. Anyway, this is going to be not used as much, but there's a reason you want to do this way. Let's say you had a vector A, which basically looked like this. I'm going to say it's maybe 30 degrees from there, and maybe it's 7 long. I don't know. Unfortunately, I can't pick numbers here that would be, easy to come up with integers. Let's say I took another vector B and say it was 3 long and it was 45 degrees. And somebody says, what's A plus B? Now, if I had my tablet, I would just move this up here and do like that. That's not, if that's 7, that is not 3. How about we do that? This is 3, and it's 45 degrees. So, if this is 30 there, I'm just trying to get it out of the way. We'll put 60 there. So I want to get things out of the way so I can draw this vector from here to here. However, I can do this. Now, I'm not a great drawer, but I can try my best to draw that roughly here, and then draw this here. So this is this vector copied over here. This is this vector copied over here. Doesn't matter, it depends on which way you like to see it. Some people like to see one, some people like to see another. It doesn't really matter. I'm not a great drawer, but here is the resultant C, which is equal to A plus B. There are two equations, two groups of equations that are always very helpful here. But let's pause here and look at the two groups of equations, and then look at the equations real closely to see when they're of value. One is the law of sines, and it's basically this. Let's just put it here. We'll do it this way. And I'll say all these laws are going to be over here to the right of this line. They're going to be associated with a funny triangle here that now looks too small. Just make it look bizarre. Here's A, here's B, and here's C. Capital A, B, and C. Now I'll make this so big that I'll have to write the law of sines cut tiny. But the law of sines is nothing more than the sine of B over B is equal to sine of little c over big C equal to sine of A over big A. By the way, you can flip that over, B over sine of B, whichever one you really like. Doesn't matter, it's the same ratio. B with A over sine A. Now, when would you use this? And let's look at this. Okay, you're never going to use all three at the same time. But let's look at a case in which you may actually say, when would I use this? And this is the part where you need to think about this. When would it come in useful? When I know two angles and one's length. Or two lengths and one angle. So I either need to know somewhere, I need to know the length and its opposing angle. I've got to know that. If I don't know these two, I cannot use this in any form. I either have to know this and this, or this and this, or this and this. Otherwise, the whole thing is a wash. It's no use. Okay, so if I know a length, opposing angle, and anything else, I can work my way through all of it. Okay, so what if I don't know that? Well, there's another law, and that was law of sines, and of course the other one here, just to keep it. The other one's law of cosines. The book will write one of them, but actually kind of we can do all three. A squared is equal to b squared plus c squared, and we'd stop there if it was a right triangle. But we can't stop there because 2b, I said b, wrote a, bc cosine of the little a. Now, this is supposing that this is the sequence. But what I can do is roll these out. In other words, I can say b squared is equal to a squared plus c squared minus 2 ac cosine. That looks weird. Cosine of the opposing b. Or I could say c squared is equal to a squared plus b squared minus 2. You know what? That's weird. I forgot to write the c, and then I read. Here's what I'll do. Let me do this. That's very annoying. So we do that so that you know that that's the c associated with this c. And then the little c there. Okay. Now, when would we use this? And this, if you stare at it, you would use this if, okay, so this is the law of sines. If you knew two of these and the angle between them. So let's look at that real close. B and C, and the angle between B and C. A and C, okay, A and C, and the angle between them. A and B, and the angle between them. Two totally different circumstances. So there are times where you have to use law of cosines to get at law of sines. And there are times where you don't even need law of cosines. It just depends on the problem, and you have to be really kind of careful about that. Now comes the part that I think is most intriguing in this class, is as we're going to do some of these problems, probably not as much today, maybe a few, but what you'll find, and what I've found over the years, there are people that see geometry, and there are other people that just don't see it. It's like that movie, I See People, or something. What was that, Poltergeist or something? I see people, you know. I don't see you. So, and so the beauty is, it's not used that much. So if you don't see these, it's not like a death sentence or anything. It's just like, it takes me a little longer to see that angle. And so then you're like, crap on that method, I'm going to use this one. Well, guess what? This is the one I use all the time, unless there's a specific problem that's useful that solves it this way. So let's just do a couple, and what we'll see is that, in fact, it's, to me, I think it's an interesting experiment in humanity. And I don't know, you know, in the old days, okay, so we have computer technology, we have all this stuff. If you look back in the 1960s to about the 1990s, there were people who saw things like this, who ended up as professors and wrote lots of papers and really made contributions because they saw things where other people couldn't see. And it's just their brains were working that way. That's taking place now in work in origami. I've had a chance to talk to a couple of people in that research area, and you realize they see the thing, their brains are wired different or something. They're just totally different. They can see things. In the okay, I'm not sure when this was, but just as a tidbit, there were people back, I believe in the 60s, there was a gentleman who was a biologist who worked with a mathematician, and they were working on like wolves, I think, or something where, you know, a pack would have this domain. And they found something interesting. So a pack of wolves live in all these. It turns out what they did, and they basically came up with a method in which they drew lines, they bisected them, and essentially they made what's essentially a mesh. And the mesh came about by basically taking a circle and picking any 3 points. So let's say I pick this point, and this point, and I draw a circle that goes through those points. Now, the funny thing is, that encompasses, those 3 points encompass 1, 2 other packs. So in fact, that's not the optimal set. It turns out you can prove there's an optimal set in which, say you pick these 3. Oh, this is a terrible circle. These 3 did not include any of the others. So they essentially created this, it's called a Delaunay tessellation. It's basically you can draw an optimal mesh from points and create triangles that are optimal out of this. And it turns out that the bisection, you create what's called a Voronoi diagram behind it, which is a diagram in which this is the domain of this pack. So this is the domain of that pack. You'll find another pack, and you basically go out, and this came from work that was in the early, I don't remember if it was the 1960s, but it was about that time. The person who was the mathematician saw things that the biologists didn't see, and they worked together and they went their way through this. It's very interesting. This has actually moved its way into finite element grid generation. If you generate, and you probably will somewhere in your career, maybe out there, where you're going to do a stress analysis or fluid flow or something, you'll be given the option of generating tetrahedral or triangular meshes, and you'll push a button, the computer will spin around, a wheel will move, and all of a sudden you'll get this beautiful mesh. They're generating them in this way. And so it turns out that we've progressed to the point where we can use computers to generate things that historically were generated from areas that had nothing to do with anything. But there were a bunch of people who saw this early on, and this is happening in machine learning too. We always talk about machine learning, always say AI this, you know. So there's a thing called large margin classifiers. A bunch of points that are, these are bad, and these are good. Oh, never mind. Here, I mean, if they're good, they need to be a different color. So this started in the late 90s, almost 2000. It's not that old. And so what they did is they said a large margin classifier. Well, what you do is you pass a line through here in which this line is optimal, and you basically look out here to find areas that will find the largest margin you can move to classify these differently. So it started as linear, then it moved into another formation where you map this space. For example, if you map this space, okay, you're going to do a straight line, okay? So you'll see this when I draw it, and you'll say, oh, I kind of see it, I don't know how to do this. So here's one set of bad. Here's the good. So here's all your good. So immediately you know, okay, bad in here, or let's just quit calling it bad and good. How about blue and black? Okay, so how about that? Because that's easier. So blue and black. And you're saying, I can't pass a straight line. What do I do? Until you realize you can map this two-dimensional space into a three-dimensional space. And what you do is you send a cone through it. So here's your cone. And here's all the blue dots mapped onto this cone. So these are on the surface of that cone. And here's all the black dots on that surface of that cone. Now can you pass a plane through it? You can easily pass a plane through this. And so that's an awful looking plane, but you know what I mean. That's why they call it hyperplane. So you took something that was two-dimensional, you turned it to 3D using some type of mapping algorithm. And once you mapped it, you can do a large margin classifier and classify them away. It turns out this is a simplification. You can find ways and you can multiple, have these weird surfaces out there in space called radial basis functions that basically just bizarre looking waves that are just generated around each point. And it turns out it won't look nice like a cone, but you can put it in 3D, or if you have 2D, you can put it in 3D and see some of that. Most of the time, you may have 5, 10, 20 dimensions, you can't visualize that, so there's nothing to do. So in fact, geometry plays a huge role in everything you do. This is one method that was come up by, I cannot pronounce his name, it was a Russian, and then since he was hired, he worked for Twitter for a while, and he went to Facebook, but he went to a professor for a while, so I don't know where he's at now. But he essentially created this in the 98, 99, wrote a paper, and then it was picked up and it went on from there. So geometry is a weird thing. So some people see it, some people don't. I don't really see it that well, actually. So let's see if we can figure this one out using these methods. Here's what I mean by you see it or you don't. Okay, hang on. Okay, so here's my little thing. Make it a little bigger. Okay. Thing that's helpful for me is kind of that. So if I do that, I can see, okay, this is really bad, but 45, if that's 45, this is 45. Let's see, that was 60 to the top of that. So this is 30. What else do I know? So now it's a matter of pulling out your angles. Okay, I know this, and I know this. Immediately, I know this and I know that. I'm in the domain of log cosine. My target is, what is that? If I can find that angle, I can solve everything. So that's why it's helpful to see what law of sines do and what law of cosines do, because it puts you in the mindset of, can I just sit here and stare at this? What the crap do I need to know? And so you sit there, well, this angle's that, this angle's that. Well, you wasted your time when in fact you saw immediately, I know these two sides, I need to know that, and I can work this out. So can we do that? I think I can get that, right? Okay, so I got 45 and 45. So if I can get the angle between here and here, can I do that? So I'm gonna let y'all tell me if I can do that. And see, there's the thing. You're sitting there looking at this geometry, and you're like, okay, wait a minute. Okay, so this is the. Let me draw this one in black because it's the one that we're looking for. All the angles associated with this C over here are unknown. In other words, we do not know the angle from here to here, here to here, or here to anywhere. We don't know any angle here associated with this line at all. So what we don't know, so I'll just do it this way. I don't know that, I don't know that. I don't know this, I don't know that. Now, can I use this blue information? By the way, it really doesn't, it's not to scale. This 30, okay, this line and this line go up here in this 30. Is that correct? And if that's 30, okay, so think about it. This vertical, got that. That's got to be 60. So there's half your battle, to me, is trying to nail that down. 60 and 45, what's that, 105? 105? Okay. So you know what we'll do? We have enough time. We'll do this both ways. We're going to check ourselves. Okay, so C squared is equal to 7 squared plus 3 squared minus, did I do that? 2 times 7 times 3 times cosine, and I'm going to say 105 degrees. Okay, I have been shown the light on a couple things. Not necessarily that it's a good or bad thing. It's just is what it is. I mean, I'm trying to find my. Okay, give me a second. Okay, well, I guess I'm using the photo map. You know that. I mean, you have that, don't you? Oh God, I'm waiting there. I'm so efficient that I do not want to calculate that. Okay. It says C is either equal to, it can't be a minus, okay? So I'm not even going to copy down the minus, never mind that. So it's going to be 8.29882. Now, before I claim that, I need to stare at this, make sure it got it. Sometimes it gets the wrong equation. The other thing I learned, if you don't put that degree, it turns it to radians. So it says that. Okay. Now let's do it the old-fashioned way. Okay, so I don't know what else to say except that this is A and this is B. So I'm going to come up with A by saying I've got a vector. Now if you don't mind, I'm going to leave A and B apart. And I'm going to do this. I'm going to say this is 30. So this is 7 cosine 30. And here's A. Here is 7 sine of 30. So I'll have 7 cosine of 30 times I, because this is the x direction. So what I'm doing now is I'm just breaking it into components. Just want to make sure I'm okay. Plus 7 sine of 30j. Now B, it's of length 3. And it's 45 degrees. So this is 3 over square root of 2, and this is 3 over square root of 2. Why is it square root of 2? Because cosine of 45 degrees equals to the sine of 45 degrees equals to 1 over square root of 2. I always use that because you might as well. So I get B equaling to, go to the right, 3 over square root of 2i. I go down, because this is going down. Now, let me kind of jump, and I'll say the C vector is equal to 7 cosine of 30 degrees plus 3 over square root of 2 I plus 7 sine of 30 minus 3 over square root of 2 j. Let's see if it can get, ooh, hang on. Let's see. Let's see if it figures that out. 8.1835I plus, let's see if I can get that all in here. Oh, I missed part of the parentheses, but it's still got it. 1.37868J. So what is the length of C? Magnitude of the vector C equal to 8.1835 squared plus 1.37868 squared. Let's see if I get this. Okay, it may mess up because it's getting part of that stuff below it, like the Windows thing down here. Oh, it ignored that stuff. Okay, so it ignored that. And I get 8.29882. I get exactly that. So it was able to ignore that. So that's good. So the biggest problem I see when it comes to these things is the identification of the angles in there. Now, what you're going to find in one of the homework sections is there's parts in there that you're going to have to find that because he may ask for an angle. But that's a faint memory, and so I can't guarantee that that's going to occur, but it might occur in one of, like, what's the angle between this and that? So, so does this all make sense so far? And I guess if it doesn't, you can rewind and watch it. If you watch the video, you can double the speed, and you can watch a 50-minute lecture in 20 minutes or so. Because generally, it takes me a few minutes to turn on the thing, get it going, start, and then make it useful. And then near the end, you're kind of. So if you plot, I don't know, each professor you can plot the efficiency as they do. They start at time 0, end at 50 minutes. Some professors are like this, so they're negatively effective there. So they just waste your time. I hope my goal is to be like this. Okay, so my goal is to do a little ramp up and be moderately effective, and then kind of go down like that. So actually, in this useful spot, instead of 50 minutes, maybe that's 40, or maybe 30. So if that's the case, you double speed, and you're looking at 15 minutes a lecture, and So if you don't get something, or if something seems weird, go back and look at it. Now, if I goof up, you're supposed to stop me. So, because I'll goof up. I mean, I used to do it sometimes on purpose, and now I find out I don't have to do it on purpose. I'll just goof up occasionally. So, I find it useless to goof up on purpose. There are people that spend all their life, what is the strategy of teaching, blah, 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 blah. Now I'm just like, I don't know. I mean, my strategy is look at the book, see what the material is, try to cover it in an overall sense so that if you read it, it's an easy read. You see it all. I remember I had a guy at Virginia Tech, his name was Leonard Marovich. He had written the vibrations textbook, massive book. We covered the whole book. Never covered that much material in a class. But what was interesting is the way he said everything. It was almost like when you read the book, he was right there. So his verbalism and the way he spoke was almost like a textbook because he had written like 7 or 8 of them. So you would find, instead of going home and studying like 3 hours or something reading the book, you could read it in 30 minutes and you'd understand it because you sat there and listened to the guy. And so I found a lot of that when I was up there. There were every person I had the course from, with one exception, had written the book for the course. So it made I learned more there than I've learned anywhere because of that. And so to me, the best thing to do, from my perspective, is try to make it so that when you see this, you read all that in the book, and it's like a quick, easy read. But my point is like the concept of when do you know to use these two? What is it that you're doing here, as opposed to the sign? And if you see that and you comprehend that, then the law of signs isn't just about memorizing an equation. It's about how you just use it. And when can you use it? And we just identified two sides and an angle between it, and boom, we know we got to go to law of cosine. If somehow we had a sine, I mean, we don't have it, but if we had this and the opposing, and then anything else on there, we'd immediately go to law of sines. So, and there are cases that you'll find in the problem sets that you have to go law of sines. More, well, I don't want to say more, but I don't know if they're equal, the way the problem is stated, but sometimes if you see that which one you've got to do first, the rest is pretty easy. Once you get the thing first, though, the other part is to think about later in your career, if you're given the opportunity to use a complex equation or a simple equation, which one would you do? The simple equation would be less keystrokes in the calculator, less things, so there's less opportunity for error. So if I had to use this over and over on a problem, I would be kind of like a fool. If I use it once, and what do we do here? We got this. The next thing to do is go immediately to the law of sines and start using it, because it has less complexity. You know, there's less keystrokes involved with finding any of this than there is here. There's less opportunity for errors to develop or propagate through your problem. So you want, from beginning to end of any problem, any course, anything you're doing, the least number of keystrokes will serve you well. So that's why you really need to learn the material as well as you can, so you can identify alternate ways of going down the path, because then you find out, one, you're taking less time to solve the problem. Two, there's less chance of an error propagating up. And so it just makes common sense. So I try to use those things. Also, you'll find me later on, I'll be using MATLAB. And why do I do that? Because why do I use Photomath? You know, so I'm not going to sit there and do all that. I mean, this thing will read and recognize that and do that and give me an answer, and I'd be just now finishing that by now, and I've already wasted a good 5 minutes talking about nothing. So, when would you actually need this as opposed to that? Let me give you a case in point, and that is, and he has some of these in there, and this does actually occur. Let's say somebody, I'm not a great drawer, but I'm going to try my best. So somebody had a hook here, it was attached to a board, and then somebody was pulling it over here, and then there's a force, say, here. And so let's say we'll just go ahead and put something on here, 10, and an angle of say 30, and this is 20, and an angle looks like 30 as well. And then you got this force that's going out here at 10 degrees. And they say, okay, so hang on, 10 degrees, and we'll call it F. Or you know what we'll do? We'll say we don't know where it's at. We don't know where it's at. But what we want is we want the resultant force to go straight up. So it has to go straight up. So then the question is, what is the value of it? Well, let's go ahead and say it's 10 degrees right now. What is the value of this force such that it goes straight up? Now, at first glance, you could say, okay, I can break these down and solve it and do all that stuff. Or you can do something like this. You can take this, okay, this is not to scale, so let me try to make it a little bit more to scale. So this is the 10. So take a moderate thing, try the best I can, and then take the 10 degrees and draw it right there. So here's my 10, this is my 20, it's the distance, that's the distance. And suddenly you see a geometric diagram that tells you, that this is going to be the distance. Believe it or not, and I've seen people do this, if you have the graph paper with the green things, sometimes you can draw things to scale and get a first run of what it is. Does that make sense? So you can draw this on the page, and then you can say, well, I went out to one of these squares and went over 3. You've seen the squares and stuff. And then you can say 2 squared, 3 squared, square root. Scale it. You'll find an approximate distance between them. You'll find that sometimes it's off by 5 or 6%. But then you can start doing your math, and you'll get an idea when you're close. And so there's a reason you get the graph. Does anybody have those green graph papers? You can also go out and use, okay, you have to pardon me, but I don't know how to pronounce it. GEOGBRA, is that it? I don't know. Yeah. Okay. Why did I hit that? Okay. Home. Okay, where do I get my thing started? Right there? No. Okay, looks a little bit different now. Resources? Profile? People? Where the heck is my app? Don't tell me they're doing. Here, let's just. Aha, there we go. As I say, this looks weird. So you can go out, just draw yourself. Okay, let's see. Do I want a segment or do I want I don't know, here. So you can draw it on this, and then you can draw another segment that's your angle. This is awful, by the way. And then you can do another one here. And you can actually do one vertical and cross them and figure out where the intersection is. Believe it or not, in dynamics, when we get to, I forget the chapter, but I think it's 16, you'll find there's a lot of geometry in that. And last semester, in the middle of it, we were calculating all these angles and stuff, and I just got tired, and I was like, I do this in CAD normally, just to find the distance, and you can do that in CAD as well. You can draw these all in CAD if you've got a CAD program, which is essentially what this is. And you can go in and find your lengths of everything, and just like that, you can get your answer. It is beneficial to guide you. It is not necessarily beneficial to completely rely on it, because you may need to use the underlying math in another problem that's a little deeper. So, you can do stuff like this, but the key is using these old methods where you just draw the vectors like that. You can see things that you wouldn't see with just math on a page. And so sometimes math on a page is great, but really sometimes I've even given tests, I'm not going to do it anymore, but given tests where somebody can solve a problem if they see it in a matter of maybe 2 minutes, and if you were going to work it out using those components, you may spend 30 minutes doing it. So, there are problems easy to create that will require you to do that. So when it comes to solving these problems, you'll see that there's some of them in there that are kind of like that. Just work your way through them. If you need to, draw it out something like this. It doesn't take that long. And I think, if I'm not mistaken, you can grab you can, oh, how weird. That's really bizarre. So you can move stuff around. I thought you could disconnect it, but he's just got segment AB. So somewhere you can look at the, I think maybe vectors are done differently. Let's see. Let's see. If I just do that, then, oops, that's not what I want to do. I want to go to the move. Then I can move those vectors. Let's see if it attaches E to D. Let's see if I attach it. It's not becoming attached. I don't feel a gravity move towards it. So you can move it anywhere you want. There's probably a way to, what does show trace do? Oh, cool. Whoa. Now what do I do? Clear all traces. Okay. Yeah. I'm not sure how you attach it. If you could attach it, then you could go in and hit a move and move the whole item. I don't know. You know, you can do this stuff better than I can do. So, have y'all used this thing before? So it's like a free CAD that is kind of math CAD, you know. Apparently there's apps associated with it too. The reason we did it in the class is this. It can tell me the length of any particular one of these lines. So it told me the length of that. So it told me that I can go out and find the distance of G. There's the distance of G. I can find the distance of F. So I can move these around now, and you'll see my distances change. And so that's beneficial if you're like playing with stuff and you want to just experiment and you're trying to get a problem done. You just want to see it roughly right off, you know. So, so it's something to play with. GeoGebra or whatever it's called. I don't know. So I guess I could let you go 5 minutes early because then I could lay on the floor and take a nap for my next class. Except I probably wouldn't want to do that. You know, people walk on the floor. I hope I was useful. If I'm not, just let me know. I mean, I'm not sure I know how to correct it, but so just go ahead and get the book, go work in the problems. If you have problems with the problems, you know, come ask me a question about them. I'll address them in class, you know, just whatever. Oh, and I guess we don't show up on Monday. So I guess I'll see you on Wednesday.